Right, welcome everyone. This is the first video in a series where I'm going to show you how to design printed circuit boards, or PCBs. Specifically, we're going to be using the free open source software called KiCad or KiCad. This video series is originally intended and developed for the Applications and Simulations course at Florida Polytechnic University. However, this will be useful for just about anyone who has been interested in designing printed circuit boards and wants to dip their toes into that field. So, to kick this off, let's talk about PCBs, printed circuit boards. What are they and why are these important to us? Well, think of the digital logic circuits that we've gone over in class thus far. Something like this. This is an OR gate circuit using a 74HC32 series integrated circuit, IC, on a breadboard with a bunch of wires and a bunch of different components that does the very basic task of taking in two inputs, ORing them together, and then outputting the output signal to an LED to show us if the output is high or low. Now, this is great, this is extremely useful, and it works for us well enough. We can take this and build exactly this circuit on a breadboard and make it look exactly like this, and it will behave pretty much exactly like what we see inside of Tinkercad. But suppose this was a product that was highly useful to a lot of different people. Maybe we're designing a circuit to send to different classes that are teaching digital logic circuits, and we want to have a circuit readily available for them to show how an OR gate works. Well, we wouldn't want to have to take 100 different breadboards like this, 100 different 74HC32 chips, and 100 different LEDs and all of the components, and hand assemble every single one of these circuits to then use or to then deliver to those students or those courses wherever they are in the world, and hope that no components fall out in transit, or hope that we didn't accidentally put a wire in the wrong place. It's not easy to mass produce these circuits or to make it so that each different instance of the same board is exactly the same. It's virtually impossible to quality control. We could also maybe put together a schematic like we saw in class, a wiring diagram basically, where each one of these components is just wired together without the breadboard. That way, there's no chance that they'll just slip out of the breadboard and break the circuit. Soldering them together is pretty sturdy. It'll hold together fairly well in transit. But then you still have the problem that you have wires and leads and little components all over the place. It's a mess and it's very difficult to keep track of. Think of your cell phone or any other electronics. We know that those are packed with tons of tiny little components, whether they're passives like resistors, capacitors, inductors, or actives like transistors and amplifiers. They're not just soldering all of those components directly to each other. What they're using instead is a printed circuit board, a PCB, that acts as a carrier for all of those components. The printed circuit board has traces built into it, which are these little copper strands, basically, on a single flat two-dimensional plane that is pre-designed for those components in particular, for those circuits in particular. So all we have to do is send off a design file to a company that can print those circuit boards, who can manufacture them in bulk, and then all of the components get soldered on in exactly the right places, and thus we have a very compact, very easily reproducible electronic device. Every single one of our modern electronics use a printed circuit board of some kind, from the motherboard in a computer or the logic board in an iPhone. I have worked for several years now with designing printed circuit boards for various purposes, whether it's my own hobby project or in industry. I've worked a lot with drone technology. I even have a few examples I can show you here. Some of the more simple ones that I've worked on are something like this is a power distribution and regulation module for a drone. This connects directly to the batteries of that drone, and it steps down that 50 volt input to 5 volts and to 12 volts on two different sets of outputs that can then run a bunch of other little sensors and motors and other devices, the flight controller that actually run on that drone. These units, I've had maybe a few thousand of them ordered from factories at this point, where all I needed to do was design the board one time and make sure that everything worked, go through that whole prototyping process, and then it was really easy to get them made in bulk. And now anytime I want more, I don't need to hand solder everything together. I can just send my design files out to those factories, those fab houses they're typically called, fabrication houses, and they will produce tons of these for me, however many I need. So that's one example. On the more hobby end, here's an example of a coaster that has an infrared sensor in the middle, where if you place your drink on top of it, it lights up a ring of LEDs around it in a programmable pattern of your choice. There's also a 2.4 gigahertz Wi-Fi antenna. This is a patch style antenna. Now, RF PCB design, radio frequency PCB design is a little bit trickier and more nuanced, but the steps that I'll be showing you in this video series will directly lead into that kind of technology, if that is something you wanted to work on in the future. A more complex design is this one. This is a companion computer for a drone. This runs a bunch of software that allows the drone to both communicate with other devices more easily through, for instance, an Ethernet switch, that is this circuit right here, or 3 different voltage regulation circuits to power external devices. It has a compute module that plugs directly into it, and this is actually 2 different PCBs that are sandwiched together, where I designed it so that, let me see if I can get the camera to focus there for you. They just use these board-to-board connectors. Oh, my camera is blurring them out, but you get the idea. And they can just plug directly into each other and function as one unit. This is how a lot of more complex systems work, where you actually stack many different PCBs together. If any of you have ever built a computer, a gaming computer for instance, you know that you have your motherboard, you have your RAM sticks, you have your solid state drive or hard drive, you have a graphics card. All of those use at least one different PCB. You put them together and then you've got maybe even dozens if you have a more complex system. So basically, you have a reason to be interested in this if you are at all interested in building electronics of your own, or selling products, or designing products for another company, or basically taking all of the electrical and computer engineering design skills that you are learning in your classes and consolidating them into an actual product that can be delivered to a user. So that's what I'm going to be showing you how to build today. Obviously, we're not going to go over anything nearly as complex as this. We're going to start out with the absolute basics, and then we'll go from there. And I'll show you how you can sort of translate those fundamental skills that we learn with a very basic PCB into more complex designs.